Chapter 4 Electromagnetic Spectrum. Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere. They are orderless and tasteless, yet you use and depend on them every hour of every day. Without them, the world you know cannot be the same. Electromagnetic radiations. These waves spread across a spectrum from very short gamma rays to X-rays to UV rays, visible light waves, even longer infrared rays, microwaves to radio waves which measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text messages, television set, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves are similar to water waves in that both are transverse waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, electromagnetic waves travel through the vacuum of space at the constant speed of light. They have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM waves are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometer. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave or cycle per second is called a hertz. Long EM waves such as radio waves have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest high-energy waves in the spectrum. So as you sit watching your television, not only are the visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone and text messages, and waves from your neighbor's Wi-Fi, and GPS units from a car driving nearby. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around, how can you possibly watch your TV? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy within wavelength from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have colors because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected and others are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eyes interpret this as the leaf being green. Our eyes see the leaf as green but cannot tell us anything about how the leaf reflects UV, microwave, or infrared waves. Scientists have devised methods and gadgets to detect the presence of all the EM waves in the spectrum. Around 1880, a British scientist, James Clerk Maxwell, developed the mathematical theory of electromagnetism. His theory predicted that electromagnetic waves propagate through space and at the speed of light, resulting from oscillating electrical and magnetic fields at right angles to each other and to the direction of propagation. So this is a typical electromagnetic wave as proposed by Maxwell. We got 3 dimensions, x-axis that goes along this direction, that's the direction of travel, the y-axis, and of course the z-axis. The electric field is represented by red. So you can see that this red is perpendicular to the x-axis, and like a sine wave, it goes above and again goes below. At the same time that the electric field is being generated, There is also a perpendicular magnetic field being generated in the blue. And as one gets bigger, the other also gets bigger. And so we have both perpendicular electrical and magnetic fields. And note that the z-axis, which carries the magnetic field, and the y-axis, which carries the electric field, are both perpendicular to the direction of propagation of the wave. Many other scientists of the time were trying to prove experimentally the existence of these waves. In 1887, Heinrich Hertz, a German physicist, designed a series of brilliant experiments to demonstrate Maxwell's hypothesis. Hertz's equipment was simple: a spark generator coupled to an antenna and a metallic ring set some distance apart. He proposed that the electromagnetic wave generated at the antenna travel through the space, and if Maxwell's theory is correct, they will induce a current in the ring and a spark will appear in the ring gap. This is a setup to replicate his experiment. We have a spark generator connected to these two wires. The electromagnetic wave will travel to the receiving antenna, where we have a neon lamp connected to the antenna. And when the spark is produced here, the lamp will glow. So we can start with a low voltage supply. And you can see the lamp glowing along with the spark. And now with a high power voltage supply. Again, you can see the glowing of the lamp along with the spark being generated. Great, and indeed Maxwell's theory is true. So electromagnetic waves are periodic changes in electrical and magnetic fields which are propagated through space. The electric and magnetic field vectors E and B are at right angles to each other and the direction of travel. Gamma rays, X-rays, UV, visible light, infrared radiations, microwaves and radio waves are all EM waves. The orderly distribution of electromagnetic waves according to their frequency or wavelength in form of separate groups having widely different properties is called the electromagnetic spectrum. The electromagnetic spectrum is described as a long line. At one end lies the radio waves, which have the longest wavelength and lowest frequency in the spectrum. A single radio wave can have the length of a football pitch. After radio waves come microwaves, which produce more energy due to shorter wavelength and higher frequency. Cell phones, radar, and microwave ovens use microwaves. Next comes infrared waves. The sun, fire, and all hot objects produce infrared waves. And while we cannot see infrared light, we feel it as heat. Visible light occupies a narrow slice of the electromagnetic spectrum between infrared and the UV light. Red wavelengths have the lowest frequency and longest wavelength of the visible light. As you move from red through orange, yellow, green, blue, and finally violet, wavelengths shorten and frequencies increase. From the visible light we move to the UV frequencies. Human skin produces burns when exposed to UV light in excess. Next, X-rays, which pass all tissues but not denser materials such as bones, making them valuable for medical tests. X-rays also have security applications such as airport baggage checks. Gamma rays produce even shorter wavelengths, higher frequencies, and more energy. Gamma rays are as small as the atom nuclei. Production and detection of electromagnetic waves. Gamma rays. Gamma rays have the shortest wavelength of all the electromagnetic waves, the size of an atom nucleus. In fact, it is so short that the rays sail through the atoms as easily as comets sail through our solar system. Created by the hottest, most violent and most energetic object in the universe, gamma rays travel across vast stretches of space only to be absorbed by the Earth's atmosphere. Deadly to humans, gamma rays are created on Earth by natural radioactive decay, nuclear explosions, and even by lightning and thunderstorms. Coronal mass ejections from the Sun emit gamma rays, followed by masses of charged particles. Monitoring these gamma rays provides scientists with an early warning of incoming charged particles that may cause disruptions in power and communication networks. The most energetic of all electromagnetic waves, gamma rays carry enough energy to kill living cells. Doctors are able to selectively use gamma radiations to destroy cancer growth. Gamma rays detectors typically contain densely packed crystal blocks. As gamma rays pass through, they collide with electrons in the crystal. The sensor doesn't directly detect gamma rays, but the charged particles created in these collisions. X-rays. X-rays are high-energy light rays with wavelengths between 3 and 0.03 nanometers, so small that some X-rays are no longer than many individual atoms. In 1895, Wilhelm Conrad Röntgen accidentally discovered X-rays. X-rays come from objects that are millions of degrees hot, such as pulsars, black holes, supernovas, or the plasma in the sun's corona. Artificially, X-rays are produced in X-ray tubes. This occurs due to electron transition between the energy levels of heavy elements, usually excited by electron bombardment. It can also be argued that X-rays originate from the action of a beam of fast-moving electrons hitting a metal target. Röntgen discovered that streams of X-rays penetrated the flesh but not the bones inside. X-rays tell a doctor which tooth to drill and a surgeon which bone to mend. In laboratories, scientists fire beams of X-rays to unknown substances to learn what elements they contain and to decode their atomic structure. This is how scientists unravel complex molecules like DNA. Ultraviolet radiation. UV radiations vary in wavelength from 400 nanometers to 10 nanometers and can be divided into three regions: UVA, UVB, and UVC. Visible light from the sun passes through the atmosphere and reaches the Earth's surface. UVA, the long wavelength ultraviolet, is the closest to visible light. Most UVA reaches the Earth's surface, but shorter wavelength called the UVB are the harmful rays that cause sunburn. Fortunately, about 95% of these rays is absorbed by the ozone in the Earth's atmosphere. UVC rays are the shortest and most harmful and are almost completely absorbed by our atmosphere. Visible light. All the electromagnetic radiation is light. Visible light is the only part of the spectrum you can see. For all your life, your eyes have relied on this one narrow band of the electromagnetic radiation to gather information about your surroundings. The sun's visible light appears white. It's really the combined light of all the individual rainbow colors, with wavelengths ranging from the violet at 380 nanometers to the red at 700 nanometers. Initially, it was thought that a prism somehow colored the sun's white light as it bent and spread as a band. Isaac Newton disapproved this idea by using two prisms to show that white light is made up of the bands of colored light. Newton used a second prism to show that the band of colored light can be combined to make one white light again. Scientists can learn the composition of the atmosphere by considering how the atmospheric particles scatter visible light. The Earth's atmosphere, for instance, generally looks blue because it contains particles of nitrogen and oxygen, which are generally the right size to scatter energy with a wavelength of blue light. When the sun is lower in the sky, however, light travels through more of the atmosphere and more blue light is scattered out of the beam of sunlight before it reaches our eyes. Only the longer red and yellow wavelengths are able to pass through, often creating the splendid sunset. Visible light is detected by the eye and photographic film. Infrared rays. When you use a remote control to change channels on your TV, your remote is using light waves. But this light is beyond the visible spectrum of light you can see. In 1800, William Herschel conducted an experiment measuring the temperature changes between the colors of the spectrum, plus one measurement beyond the visible red. When the thermometer registered a temperature warmer than all the other colors, Herschel had discovered another region of the electromagnetic spectrum, infrared light. This region consists of short wavelengths around 760 nanometers to longer wavelengths about 1 million nanometers or about 1,000 micrometers in length. We can sense some of this infrared energy as heat. Some objects are so hot that they also emit visible light, such as fire. Others, like humans, are not as hot and only emit infrared radiations. We cannot see these infrared waves with our eyes alone. However, instruments that can sense infrared energy, such as night vision goggles or infrared cameras, allow us to see these infrared rays from warm objects like humans and animals. Infrared can also reveal objects in the sky that cannot be seen with optical telescopes. Microwaves. With wavelengths ranging from 3 centimeters down to 1 millimeter, microwaves fall between radio waves and infrared waves. Microwaves can pop your popcorns, catch your speed, carry thousands of phone channels to speed your calls, and help us learn about our universe. Microwaves are used in Doppler radar, which is widely used for short-term localized weather forecasting and what you see on your TV weather news. Satellites have revolutionized weather forecasting by providing a global view of weather patterns and surface temperature. Different wavelengths of microwaves grouped into bands provide different information to scientists. Medium-length C-band microwaves penetrate through clouds, dust, smoke, snow and rain to reveal the Earth's surface. Finally, radio waves. Radio waves are the longest and contain the least energy of any electromagnetic wave. While visible light is measured in minute fractions of an inch, radio waves vary from about 19 centimeters, about the length of a water bottle, 2/2 the length of a car, ships, mountains, all the way to monstrous waves longer than the diameter of the Earth. Heinrich Hertz discovered radio waves in 1888. The first commercial radio station went on air in Pennsylvania on November 2, 1920. It was later discovered that stars and other space objects radiated radio waves. Radio astronomy was born. However, scientists need large antennae to detect weak, long wavelengths from space. Scientists can link the signals from an array of separate radio antennae to focus on tiny slices of distant space. Such arrays act as a single immense collector. Many of the greatest astronomical discoveries have been made using radio waves. Pulsars, plasma clouds, which are among the largest objects in the universe, and even quasars. Radio waves fill the space around us to bring entertainment, communication, and key scientific information. You can't hear these radio waves. When you tune your radio to your favorite station, the radio receives these electromagnetic radio waves and then vibrates the speaker to create the sound waves we hear. We now look at satellite communication. A satellite is an artificial body placed in an orbit around the Earth or another planet. The communication satellites relay around the world telephone and fax messages, TV programs, radio signals, and so on. But how does satellite communication happen? The process of communication begins at any Earth station. The Earth station is an installation designed to transmit and receive signals from a satellite in orbit around the Earth. Earth stations send information in form of high-power to high-frequency signal to satellites that receive and then transmit the signal back to Earth. These retransmitted signals are then received by other Earth stations in the coverage area of the satellite. The area which receives the signal from the satellite is known as the satellite footprint. The transmission system from the Earth to the satellite is called the uplink, and the transmission system from the satellite to the Earth station is called the downlink. This is a schematic representation of the principle of satellite communication. To avoid confusion, the uplink and downlink frequencies are kept different. Before designing a satellite communication system, we must decide the orbit in which the satellite will be placed. Orbits are of three types: geostationary orbit, polar circular orbit, and inclined highly elliptical orbit. In geostationary orbit, the satellite takes 24 hours to circle around the Earth once. Since the period of revolution of the satellite is equal to the period of rotation of the Earth, the satellite appears to be stationary in the sky. For that reason, this 35,900 kilometers high equatorial orbit is called a geostationary orbit. The entire Earth could be linked or covered by communication network if three geostationary satellites are placed at the vertices of an equilateral triangle. Each of the satellites covers a third of the globe. A polar circular orbit is placed 1,000 kilometers above the Earth's surface. It passes over the poles with the angle of inclination of this orbit being 90 degrees. It covers the whole Earth in every 12 hours. Satellites used in weather forecasting are launched in polar orbit. An inclined highly elliptical orbit is used in establishing communication with regions at higher latitudes. The angle of inclination is 63 degrees. Radar, named from a system of radio detection and ranging. Radar transmits short pulses of radio waves that scatter outwards, basically in straight lines. When these waves hit a surface like a vessel, some of them are returned. By measuring the time difference between transmission and reception of the reflected waves, the distance to an object can be calculated. The direction in which the scanner is pointing when it receives the reflected waves represent the bearing of the object. Antenna. Antenna is a vital component of any communication system which is used at both transmitting as well as receiving end. It is basically a conversion device and is made up of a long conductor. At the transmitting end, it converts electrical energy into electromagnetic waves and then radiates into free space. At the receiving end, it receives electromagnetic waves and then transforms them into electrical signal, which act as input for receivers. There are two types of antennae: dipole antennae and dish antennae. A dipole antenna is only directional and used in transmission of radio waves, whereas a dish antenna is a directional antenna used typically in radar and satellite communication. Microwaves and cooking. A microwave oven has an electronic vacuum tube called a magnetron, which produces short waves of microwaves. In most such ovens, these waves travel through a waveguide, a rectangular metal tube, to a star, a fan-like device that scatters the waves around the metal interior of the oven. The waves bounce from wall to wall until they enter the food. Water molecules, which are contained in most foods, are dipolar. That is, they have a positive electrical charge at one end and an equal negative charge at the other. These dipolar molecules act as tiny magnets, and as microwaves pass into the food, the molecules are pulled first in one way and then the other by a magnetic field created by the waves. This back and forth motion of the molecules occurs nearly 2.5 billion times a second. This rapid vibration causes friction between the water molecules, which produce heat. And so, in conclusion, although the electromagnetic waves differ greatly in their wavelength and effects, they share the following properties. 1. They travel through space or vacuum with the speed of light, that is 3 × 10⁸ meters per second. 2. They do not require a medium for transmission. 3. They are all transverse waves in nature. 4. They undergo interference, reflection, diffraction, refraction, and polarization effects. 5. They possess energy in different amounts according to the relation E is equal to hf, where h is the Planck's constant, given as 6.63 × 10⁻⁻⁴ joules second, and f is the frequency of the wave. Finally, they carry no charge, and hence they are not affected by electric nor magnetic fields. Let's take an example. If green light has a wavelength of 0.5 micrometers, calculate the energy it emits. Solution: speed is equal to frequency times wavelength. The speed of all electromagnetic waves is 3 times 10 to power 8 meters per second. From this relation, frequency is equal to speed over wavelength. Convert that wavelength into meters, we shall have 5 times 10 to power negative 7 meters. So frequency is equal to 3 times 10 to power 8 over 5 times 10 to power negative 7. That gives us a frequency of 6 times 10 to power 14 Hertz. Energy is equal to HF, and if you multiply that, you shall get 3.98 times 10 to power negative 18 joules. That is the amount of energy emitted by the light.
X-rays were discovered by Willem Conrad Röntgen. He had photographic plates which were kept in a light-tight container so that daylight could not get to these plates. These were kept in a drawer. For some reason, Röntgen actually decided to develop these plates after having played with his cathode ray tubes. Now, remembering the light from the tubes had no way of getting to the photographic plates. Yet, when he developed the plates, they were exposed. There were markings on the plates that shouldn't have been there. He had then discovered what we today call X-rays.